I'm Tom Chuparkoff. I'm a project manager with a sports and entertainment firm, Populous, based out of Kansas City, Missouri. And Steve Lewis is a structural specialties leader for Walter P. Moore, renowned structural engineers here in the United States. Today we're going to talk to you about parametric design and project execution. That's going to surround itself around Daly's Place, which is a covered practice facility for the Jacksonville Jaguars, and then a 6,000-seat amphitheater that's all-encompassing with the same program. But first, before we get into the technical components of it and the process, I feel like I really need to set up the project. As you read in the intro to the class, we didn't necessarily use new software, and we didn't necessarily recreate the whole production wheel, but we had an incredibly complex project and an intense schedule, and we just reinvented our workflow and used our modeling software in new ways and integrated ways. So that being said, about a year and a half ago, the Jacksonville Jaguars contacted Populous and another sports architecture firm to kind of do a little mini charrette to envision what an iconic covered Flexfield and amphitheater could look like and how it could systematically attach and be a part of the existing Everbank Field football stadium. Shahid Khan is the owner of the Jacksonville Jaguars, and if anyone knows him or if anyone knows of him, if you don't, you should look him up. He's he's obviously a billionaire, but he's very interesting, and he's an industrial engineer by nature. So the parts and pieces and how the building went together, from an owner standpoint, was very unique because that's what he liked the most. That's what was sexy to him. So when he asked us for an iconic design, in fact, to be honest, we submitted like 2 or 3 designs before this, and none of them worked for him. The budget was, all-in number of the budget was about $60 million, and the projects that we kept showing him for $60 million, the projects we kept showing him that cost $60 million, he didn't like. So I mentioned a mini design competition. So then he said, well, listen, you guys got to come back and you got to show us a building that's iconic. He lives in Chicago, but he's from London. He owns a Fulham football club overseas. He takes the Jaguars to London every year, so he's very international. So he wanted it to be prevalent and relative to the international circuit. So he gives us the task to build this building. It's got to be iconic. It's got to connect and have all these unique programmatic pieces. Oh, and by the way, you have to be done by May of 2017, or actually April of 2017. So Walter P. Moore and Populous started to pre-collaborate before we had any schedules or any contracts or anything established, and we were brainstorming on how that would look and what kind of schedule that we were confronted with. So this is a preliminary, just a kind of a diagrammatic schedule, just kind of define the time period that we're talking about and why we had to reinvent our workflow and our software usage. So basically, the top of the bar just defines a 6.5-month design and construction document phase. Within this period of time, along the black diamonds, you see we had different bid packages and different early release packages. So first and foremost, right after schematic design in April, we had a 7-8 package that was bulletin 2, which was mill order. So basically, by the time we're not even done with design development, Walter P. Moore and Populous were asked to turn over a Tekla model, a materials model, to our fabricator for fabrication so that they could be ready for building in August, 3 months after, or actually right after our GMP, which is our final construction documents. And then that would give our contractor, which was Hunt with construction, AECom, and a local partner, Dana's Construction in Jacksonville. So knowing that we had this constricted period of time, this highly complex project, we needed to find a way to define our process, define the people who were doing it, and defining the programs that we're going to use to execute on this. Now, we all talk about collaboration. Everyone collaborates. We get it, right? But how do you take a project and how do you take a distributed workplace? Walter P. Moore used offices in Los Angeles, Kansas City, and Tampa, right? Populous had people in New York City and in Kansas City. We had engineers all over the place. We had our, the construction manager was in Indianapolis and Jacksonville. We ARUP, which is out of New York. So we had to figure out how we could define a workflow and a work plan and create it in a more integrated way. Now, Steve likes to refer to this as the London Underground map because it's like all over the place, but this is a cool diagram because it shows the 18 different entities with the 3 different relationships. This project was a design, bid, build project, but the minute we signed a contract, all that went out the window. It was definitely design assist, it was IPD, it was all those things. So what this shows is Populous is at the top of the page in New York and Kansas City, and then under that we had Walter P. Moore, and again we mentioned all of their offices, Los Angeles, New York, Kansas City, and Tampa. And then the map just kind of shows how much of these collaborations and how much of these communication strands are advisory versus contractual versus prior collaboration. And in other words, when we were asked to take over the ownership of the materials model, the fabrication model, obviously the first thing we had to do is change everything, open up a dialogue with Banker Steel, who was the fabricator, and Walter P. Moore and Populous had to have that conversation. We weren't obligated to do it, but we knew we had to do it. So, you know, this essentially blurs the line. So the other thing, as Steve and I were having drinks last night, we were talking about, we don't endorse this process, right? Like, we were put in a position where we had this fun project, this very unique project that was important to us, and we had a period of time to develop it and execute it. Now, if it ever happens again, I think that all our bosses will be like, don't agree to that, because it was just so intense. So once we defined the period of time, we had our schedule. We know when our drawings were going. What bid packages we were going to target. But what we did was, actually, Walter P. Moore authored this schedule on the left. And what it does is, you don't need to read all the red and blue stuff up top. It's very linear in nature. We were doing things before other things were done, taking tremendous risks. Just making sure we're talking to people and be like, all right, well, look, if we do that, this has to happen next. And just making sure people knew they were accountable. I mean, we really kind of set a table and we said, look, these 6 things have to happen. And if one of your things aren't happening, you need to let everyone know, like, as fast as you can. And then, but what this defines is it took our schedule and our design time. Now, I'm not talking just schematic design development. I'm talking fabrication, right? I'm talking Walter P. Moore developing the Tekla model within 19 weeks. And halfway through that 19 weeks, these guys are building a steel model, taking the Rhino model, putting it in Tekla, doing the Tekla model, providing shops, having dialogue, flying out to Lynchburg, Virginia, meeting with Banker Steel, and really trying to figure out the best way for us to take our model and our models and then convert it to the Banker Steel for fabrication. Fabrication took 19 weeks, and then erection took 18 weeks. I'm talking erection of 160,000 square feet of area, which encompasses a 94,000 covered indoor football field and a 6,000 seat amphitheater connected to the stadium. So the workflow, right? I didn't say everyone's done all this stuff, but we did it, and we did it all in a condensed period of time, and we reinvented the way that we were working. So this diagram shows the different parts of the 5 little wheels of action. Populous and the design team, including Walter P. Moore, because that was part of the prior collaboration on the onset. We come in, we started designing we defined what was a priority, right? We knew that it wasn't about the floor plan right away. We knew what the floor plan basically was going to be. We knew what the program was going to be. But we had to start down from the top. We had to start with the iconic nature of the roof and how the roof was going to be, well, iconic, right? And that's all. I know it's totally subjective, but in this term, Shad Khan had his version of iconic, and we knew that we were going to do something. We had to do something different than he's never seen before. So we took 3,000 tons of steel, and then we hung the roof from it, and then we built a fabric box around it, and then encase all that with concrete. So now we knew that we're hanging a roof from the structure, so from inside the space you're looking at the waterproof environment with all of the steel penetrating. Obviously that's a task in its hand. So we started the model out in Rhino and Grasshopper to define the process and what the shape and the form was. That Grasshopper model was currently shared with Walter P. Moore on a regular basis. That process went through optimization. Walter P. Moore could help us rationalize cost. Obviously, I mentioned cost was a big deal. We were sitting at a $60 million budget. We were well over that just based on the fact that it was a competition. And then we knew we had to tighten the reins, right? So we knew we had to work on the surface area, the planar area of the building. We knew we had to work on the surface area because it's undulating. We knew that we had to work on the tonnage and the curved members versus segmented members. We knew we had to work on drainage and wind upload and all that. So this all happened within the optimization window using our Rhino model back and forth with the Grasshopper scripting so they could track all the nodes, which we'll get into in great detail in a minute. All that went back through Populous and through, well, at this point, it might even have had some specialty. A banker might even have been in the conversation to an extent. So again, taking our Rhino model, so we use Rhino pretty much to package everything out to share it. Admittedly, we did not use BIM 360 or C4R. It's not because we didn't want to. We were just going so fast that we literally had a script that we kept sharing back and forth and a model that was just actively being built all the time. So the Rhino was the encompassing package that was shared. And then going through our analysis, which Steve will get into some of the things of how we use analysis, using Excel especially is very powerful in this project because Excel can share information, right? And we talked about good data, so as long as you have good data, you can do a lot of things with good data. And then back to convergent with a Tekla model that Walter P. Moore used, and then we took our Rhino model, converted Tekla for Rhino so that we could illustratively show it within the construction documents for permitting, and then that was sandwiched into the production model. This is just a good diagram. It's very illustrative of the parts and pieces, right? So starting here from the left, I mentioned we had the roof hung PTFE roof, a shear fill product, if you're familiar. And then we used our Grasshopper to really organize the process, right? And how, to me it was real important that it was organized so that we had multiple people in multiple different places using the same Grasshopper script and Grasshopper platform. It's the most, we always talk about BIM plans, right? This is a thing that should also be a part of that. When you're writing a script or when you're organizing a model, we use this so each section in the blue, you chase it up and then you know exactly, where you're inputting your geo inputs and how you're going to modify the primary trusses versus the secondary trusses. In this case, we had primary trusses, bridge and trusses, and then these V columns. So we kept a very clear outline within our internal communication, our BIM plan, if you will, that kind of try to communicate how you control and draw all this stuff. So the design, right? So let me just spend real quick and just tell you this design. So the iconic design is performance-driven aesthetics. This thing is for the Jacksonville Jaguars and the city of Jacksonville. It was a 50-50 venture. So obviously Jacksonville, it's a coastal town of northern Florida. It's bordering St. John's River, a lot of estuaries. It was an old shipyards town, so it's very industrial. It's got 3 of these really beautiful these bridges. They're all different colors. They're all illuminated. It's part of their vernacular, right? So you have this culmination of estuaries, these bridges, and the landforms because the sea dunes, and it's a beautiful place. So Shad likes that, right? So we use that as our driver. And then we also knew from a programmatic standpoint, it had to influence sport. It had to invoke their brand. It had to be a part of who they were as a growing team. Finally, they're good, so that helps. We like to blame it on the cover at Flexfield, too. And it had to entertain. So now Shad Khan's trying to blend 2 programs. Nowhere in the National Football League is there an amphitheater and an indoor training center that systematically unite, which is a one of a kind. Therefore, there wasn't much precedent we could take from it. We did tours of amphitheaters, and we went all over this country looking at half of the country, the eastern side of the country. And we really tried to find a way to bring in entertainment. It obviously had to interact. He wanted people to move through the building. He wanted it to be iconic. He wanted it to be a place, even if there's no show, he wanted people to come and hang out. Again, we talked about sculpture. So these are all the drivers that we showed to kind of get them going. We talked about performance from a building, how it was supposed to operate, but how does the building, all these parts and pieces we just talked about, we had to figure out, so the existing football stadium is connected by the amphitheater. The amphitheater is a 3-level amphitheater. This section, when we did a sightline study and we were trying to define how close everything goes, we studied a lot of different little boutique theaters, right? Because 6,000 seats is not that big. We're not talking a big, and we're talking Broadway, Radio City Music Hall type of facility. So what we did is we took the Radio City Music Hall, kind of party, if you will, the section, and we really kind of organized around that. So the sightlines in this place are incredible. And then that had to abut up to a indoor practice facility. And then of course there's public and private security reasons that we'll get into. So that shows the kind of the section. And then here shows the existing stadium, the amphitheater, and the covered Flexfield with the roof. One thing to note is the Everbank Field has the largest scoreboards. Actually, did Atlanta just take that claim? So let's just pretend that they're definitely one or two, but they had their scoreboards are like 120 feet long on both sides, and they got these very enormous, the scoreboard is this guy right here. And then they have these really accentuated steel trusses to mimic the bridges. So our building, when I said we flipped it, right, we put the roof on the underside of the structure. We really wanted to complement that and do it in a good way. So again, we have the estuary, how the building flows, how the program flows. We had the exposed bridge with the roof membrane, and then the performance deformation. So we from a drainage strategy, passive, like for cooling. The building's not air conditioned, right? So we had to create a breezeway effect, so the winds and how the water drains off the building. Obviously, you can't just put scuppers and downspouts around this whole thing because it's a fabric roof with fabric walls. So we had to be very careful on how we shed the water off the ground or onto the ground. So this shows some parts and pieces that we really started to analyze. So then Walter P. Moore came in and we started building the model and we started doing analysis and we started to really push the limits on our software. We knew what was important to us. And this is just an image of an elevation of the front facade of Daly's Place showing the scoreboards in the background. One thing also is important is that the south side and the north side, you see, well, I guess I could just, sometimes I forget I'm short. So the big opening in this area, these are large aircraft hangar doors, so they open so that on both sides basically, so when they're in the covered flex field, it can be an outdoor environment, right? Because they don't want the football team practicing in air conditioning because they don't play in air conditioning. But they have the doors for security reasons. Here's a rendering that we did of the amphitheater. So the covered flex field is over here, and the football stadium's over there, and it's sandwiched in with an amphitheater. So you have the lower bowl, you have 2 upper rings of seating, and the stage happens here. You see the inside of the roof. We put the roof again on the underside, which Steve still thinks we're crazy. And then you see these light ribs, which is secondary trussing that we use just for, we'll hang stuff off of, essentially. And then the proscenium for the stage. And then the inside of the covered flex field. So this is a scenario where, from a design standpoint, we really wanted to, again, we wanted to be complementary of the industrial nature of Jacksonville, but on the inside it was about sport, right? You go to a museum and the museums are simple. The museum's about the artwork. It's not about the architecture on the inside. This is the same thing conceptually. So we really wanted it to be clean. We wanted it to be a big fabric box that glows. So you see, there's some program, we have goalposts and we have big ass fans. Those are really what they're called. And then the rest of the stuff is just fabric. And I have some pictures of this in a minute, but at the end of the presentation. But this is what we sold him, and this is what he really liked. So now we have to figure out how we make a building like that watertight, how we make the building drain properly, how we do it in 12 months, which is still crazy. Here's a rendering of the building from a ISO. So you see one of the bridges. The other bridge I showed you was a green one. There's a red one. There's a blue one. The stadium's very industrial. It's a lot of steel trusses. So the framework of the amphitheater. This is the covered flex field. The amphitheater's back in here, and then the Versade wall fabric, which we, by the way, first building in the United States to use that fabric. So part of our 12-month period, we then had to go and get code approval for a brand new product out of Germany, which was interesting. We had some optimization strategies. We knew that we had to reduce the building width, the surface area of the roof as much as possible. We had to find ways to constrict the bowl so that all the cast-in-place concrete was as efficient and economized as much as possible. We find out ways to phase. Normally we don't get into means and methods, but in this project that was a big part of our thing. We had to figure out what needed to be drawn, what needed to be modeled, and how we're going to build it, so that even when Steve will talk about the shore and interaction, that was a big part of our design, big part of his design, based on how they pick everything. So surface undulation, how it's all reinforced, and all exposure. So we set up a bunch of stuff that gave us priorities, so that when we did analysis, we knew what we were looking at. This just shows from the base scheme, we originally started at 192,000 square feet of top surface, and we ended up down to about 157. Just through this analysis, we were able to do it without losing any time. I mean, I would be so bold to say that we would not have been able to do this without the way that the softwares and the analysis that we used in that period of time. So then we really got into our leverage and our capabilities, right? So how do we take, we have a Revit model, we have a Rhino model, we have all the Grasshopper script and the support in it. And then, so from that point, the collaboration between Hunt, Danis Construction, Walter P. Moore, Populous, and Banker Steel, we really had to dig into the parts and pieces, right? So Steve's going to talk to you a little bit about some of those parts and pieces that were interesting.
Can you guys hear me? So yeah, just to follow on from Tom, I think there were three kind of unique things about our workflow, I think, which kind of describe the parametric design. I mean, one thing we had to do very early was to use interoperability. I think everybody understands that. I think the way we approached it was to obviously use Excel as a container and really come up with a neutral file format that we could share between ourselves, Populous, and the other design partners. The other unique thing I kind of thought was good about this project was we all talk about digital workflow, we all talk about Grasshopper, but how do you share that digital workflow? So we had this concept, well, we could describe it as a recipe, and by sharing recipes, that means somebody can take somebody else's digital workflow and kind of repeat it, and you can see, for instance here, this kind of describes the inputs, the outputs, and all the files associated with that particular workflow, and then all of that information is kind of stored in a recipe. The other unique thing, I think we kind of embraced interoperability, and we try to do that in a neutral file format. So the idea of really coming up with a CSV-based file format that is able to be shared between our different programs. So as the engineer, I'm kind of mainly concerned about the primary structure. So that's an analysis done in a program called SAP, very similar to Robot. In terms of fabrication, Tekla is kind of a standard tool. It's a high level of accuracy. We can share that information with the steel detailers. For documentation, using Revit. And then kind of for the design driver, we were using Rhino. So how did our process work? So the first thing, similar to what Tom mentioned, was we started off with a design surface. So this is given to us by the architect. And what we do then is from that driver, we then instantiate what we think is a suitable framing scheme. So this is a sketch of my boss's idea of how to frame it. And then we start exploring these different framing options. Another key thing, we kind of did something crazy on this project in that we put fabric on the bottom. And because of that, you have to be very careful about the drainage. So we went through various iterations with Populous to kind of massage that geometry. And one of the things the digital workflow told us here was, okay, can we adjust the geometry to ensure we get drainage? So that was, I would say a good parametric exercise which really informed the design. And in terms of the engineering, so this is the hierarchy. So at the bottom we have what we call the V columns. So these V columns provide both vertical and lateral resistance. Around those columns is the facade wall, which is actually tensile skin, and it's supported by a backer steel structure of about 60 feet. And that's used to transfer wind loads. On top of that, we have the secondary steel, and then below that, we have the ETFE, and then on the top, we have the primary structure. So for each of these kind of structural pieces, we had an associated tool that we used. So obviously for fabric secondary, we used a tool called GSA. SAP was generally used for the primary structure, and then we used Revit as the medium to pull all of these pieces together and coordinate between ourselves and Populous. And again, just to really explain how did parametrics work on a project. So this is just a typical exercise we would have to do. So taking the inputs, which is a design driver surface from Populous, taking our kind of database information of what secondary steel size we need. We then set up a recipe to kind of push that information into Grasshopper and then write our own scripts, user objects, custom components to pass that and push it straight into the analysis model. So the task we're trying to do here is take Populous' design surface, rationalize it to a series of meshes, instantiate the secondary steel, and then also introduce the fabric seaming, which is also important when you analyze fabric. You have to make sure the seams are the right direction. Another thing we utilized parametric workflow for was trying to get a high fidelity of wind load. So there's two ways you can do this. You can go by code, so you can open a book, you can rationalize this crazy geometry and try and work out what your wind loads are, which generally is going to be conservative. Or the other approach is you get a wind tunnel consultant involved and you try and map these wind pressures to your analysis model. So we had a workflow here where we could take an Excel data sheet from the wind consultants, and then we mapped it to the design surface, and then through our workflow we pushed it through to our analysis model. The key thing here as well, like Tom said, is we already bought into a weight to steel. So by having more fidelity in our analysis, we can make sure we're keeping that steel tonnage constant through the design. So this is a high level of fidelity, but I think in this case it was worth it.
Yeah, and I would like to also add, I mean, the secondary benefit of this was our owner was trying to insure a building that's never been done before. There's obviously, their insurance company was asking all kinds of questions. Your roof is 160,000 square feet of fabric. What happens when a panel collapses, right? What happens? How can you assure me that, Hurricane Irma came through, and I'm proud to say we had not one tear or loosened fabric. So this also allowed us to be very conscientious about the realities of building construction on a coastal climate. So we got a lot of value out of this. And the wind engineer was BMT out of London. So predominantly our New York office was coordinating with them to do that.
Yes, just to talk a little bit further to what Tom said. So the other thing we have to think about is, we have the fabric on the structure, and we have to make sure that the strength of that fabric can withstand, some of the wind pressures, which is similar to, we had that hurricane recently, which is pretty serious. And as an engineer, what we try to do, we try and present these results graphically, so we can have a conversation with a client and tell them, okay, we have some issues here in that the capacity of the fabric may actually be not as great as the demand. So what I mean by that is we always compare demand versus capacity, and provided your capacity is more than demand, you're okay. So this is a graphical illustration to make sure the fabric is working for the applied wind loads. And again, we also have to sometimes consider extreme load events. So that is what would happen, which we're pretty confident it'll never happen, but what would happen if a fabric panel failed. So the way we approach that is to identify some key zones and really remove the fabric from the analysis and just see what it did to the fabric stresses. So this isn't an actual, what I would call a service load case. This is us saying, okay, if a panel failed, are we comfortable that the steel supporting the other areas and the fabric don't get compromised? Because if you take a panel out, the forces have to go somewhere else. And then, as Tom said, we're moving at 1,000 miles per hour in this project, and we have to look at ways to save tonnage. We have to look at ways to minimize risk. And this is an example here where we had to really see, well, in our original design, we had these transverse secondary steel members. And the potential issue with that is there's more opportunity for problems with waterproofing. So, one study we were able to do very quickly and parametrically is we had the analysis model set up, and then we could just explore options of taking the steel out. Is it compromising the fabric strength?
I mean, there's other variables too. It's like Banker Steel. So, February, we said, hey, we have this building. There's 3,000 tons of steel coming your way, and we need it in 6 months. And I mean, those people, most of the time, people already have a backlog, right? They're not, A, they're not available, B, they're not interested, and C, they just don't have the material. So there was a period of time, because we're all undulating in steel, there was a period of time where look, we can't get all that curved steel, or we can't roll all that steel. Can we find ways to incorporate segmented steel without compromising the design? So that was another part of this analysis that happened concurrently with us just developing and modeling our project.
So, yeah, another key problem here is we're moving very fast, and we're having to almost run 2 parallel models together. So the way we approach that is to consider the modeling of the secondary steel and the fabric in a tool called GSA. The primary steel was done in SAP, and these 2 analyses were happening in parallel with one another. And at some point, we have to pull them together and make sure that the forces imposed from the secondary steel on the primary is acceptable. It's not overstressed. And in terms of the primary structure, we have what we're calling the longitudinal trusses. So I think the span typically of these was about 300 feet. And the load from the longitudinal trusses are then resolved into what we're calling these mega trusses. In terms of the fabric stress, that is carried and resolved into the transverse trusses, which then get carried back to the longitudinal and back to the mega trusses. And really, what we're doing here is we've already agreed on a steel tonnage, which we've bought off on, and we're trying to maintain that tonnage as we explore in all these different design options. And this kind of gives you an idea of some of the optimization required. Every single color represents a different steel section. So, there's very little regularity in the steel shapes and weights.
The only perpendicular steel was like the column and the foundation plate. Everything else of that was some obtuse angle, right?
So in terms of the parallel analysis, one thing we found useful for with the parametric design workflows we had is not use it just as a means of building geometry, but just use it as a means of QC in our model. So simple thing we're doing here, we're just making sure that the applied load applied to our GSA model, which is a secondary fabric model, ties up with that load. You then put on a parallel model, which is in SAP. So quick QC check, within your workflow, maybe you have a point cloud is a vector associated with a point cloud, which is your force. You can very quickly sum them up. That gives you your total load. And then what we had to do then is, in a secondary steel model, we have a whole point cloud of vectors representing a point of application of force. So we have to map that to our analysis model. So workflow was very good there. We weren't actually building a model, but we were using it to kind of transfer information and make sure the fidelity was pretty high. So what that means is we're just making sure we're tracking the ID of the vector in one analysis software to another. So that's almost like Revit. You have unique IDs. And that allows the user or the engineer in the primary structural model to make sure, okay, you got a one-to-one relationship. I'm happy that our forces have been translated correctly. Then this kind of gives you an idea. This is just for one load case. So for each load case, there's probably 4,000 point reactions. Each one is different. We're going to this fidelity because we've already bought off on a steel tonnage. So we want to make sure that we're taking as much opportunity of parametrics and digital workflow as possible to make sure the fidelity of the data is 100% accurate. The other thing to think about is it's not always just about optimizing. You've got to think about structural performance. So the other key driver we had to always meet was to make sure the structure was kind of within what we call, how do you say it, a frequency. So that's an idea of how much a structure vibrates. So a low frequency means it's really soft. High frequency, it's stiff. So as we're going through these design explorations with Populous, we're always producing kind of a summary sheet which just tells us, okay, yes, we've optimized the steel, but is the structure still stiff enough? And then again, kind of setting up a design matrix where we may explore different design options with Populous. For instance, can we remove cables for bracing and introduce rods? The simple issue there is if you use a rod, you can't get the same amount of tension, and the frequency of your model may actually go down, right? So, I mean, I would say working parametrically and with an architect and engineer, you can sometimes have to set up more performance-based criteria that aren't immediately obvious when you start the design. And then what this shows, again, is this idea of always tracking the model, always tracking the weight, always tracking the frequency. And when we started the project, I think we agreed to a tonnage of about 3,729 kips. And, you know, just for these 5 different iterations, you can see, you know, we managed to reduce that, but still keep the stiffness up.
Yeah, and this is another application where Hunt Dana's Construction, our CM, you know, they were leveraging us and our tracking, our parametrics also, because there was 2 prices they were getting from a steel fabricator, right? There's one price for the more complicated stuff, and then there's a different price for the, you know, easy stuff that they can get off a line. So when we were going through this, you know, we worked in tandem with our CM to make sure that the numbers that they thought they were tracking, that the Banker Steel was saying that they're ordering, that we could always keep those 2 things simpatico, if you will.
Then the other piece we got involved in is not just the engineering, but we have to make sure that all these pieces can come together. We have to make sure we can fabricate it. And the complexity of the structure means there's a high level of detailing required. That is, you know, how does a fabric get connected to secondary? Do we have the waterproofing?
So this is an area where we blurred the line. Remember, I told you it was a design, bid, build process, but we just completely threw out the window as soon as we got going. Walter P. Moore and Populous actually took on the onus of the shop drawings for the fabric. So instead of us doing a structural steel layout, giving it to the contractor gives it to the fabricator, they do shop drawings, they give them back to us, and we look at them. We did the shop drawings for them. So they basically moved money from the construction budget. We wrote an ASR, an architectural service request, to do that service on the front end, so that Walter P. Moore and Populous were doing that from the onset. And then furthermore, when we did the fabric, so then we hired there's a company called Structure Flex that did all the fabric roofing, and additionally, instead of them hiring somebody else to do the detailing in shops for them, they hired Walter P. Moore to do that, so that they were one entity to do everything. So there was no shop drawing process. Their drawings from the onset were the fabrication drawings.
And so the way we approach that is that we have the idea of this kind of common file format that we're distributing between different tools and between different partners. And, you know, very early on, we kind of set up a way of IDing a lot of these elements and making sure we're able to track that ID as we go through different programs. I mean, this is kind of useful because, you know, if you're looking at stiffening a structure, maybe you want to stiffen 2 members, you want to make sure you can track which member you've upsized, and you want to make sure that goes through to the fabrication model. So here we had a workflow where we would push the information from the Excel database into GSA, and that information flowed through to the design model in Rhino, which kind of is indicating what these IDs are. And really, that also helps with documentation. I mean, as Tom said, there's no how do you say, no real grid lines on this project. Everything is organic. I don't think there's any symmetry in it. There's just nothing. And the only way we can really approach that is to kind of document it in terms of identifying unique IDs or node points, and through an indexing strategy be able to coordinate those geometrical data points between, you know, the fabricator, ourselves, and also the fabric contractor. And really this gives you a sense of the fidelity of some of the fabrication and digital modeling we had to get into. So the image to the left is really our Tekla model. This is an image of the mast being fabricated in the shop, and then this is how it all came together in the field. And you can see, you know, you got a pretty good resolution between this and the digital. So this is all done by Walter P. Moore, running in parallel. And again, this idea of indexing, the importance here is for this connection, it has to be engineered. So that means we have to be able to transfer our connection forces from our analysis model. And obviously, if you know what the IDs or the index are of those models, you can easily extract the forces. You know, you got coordinated with the detailing. And again, you know, we have our kind of basic database of IDs, section shapes. We kind of bite off between ourselves what information we're going to carry between the different platforms. And then we're able to very quickly push that information, say, from a SAT model into a Tekla model, obviously utilizing the API, writing your own custom object, or probably wouldn't be a custom object, it'd be your own custom component. And then that information was pushed directly to a Tekla model, so every element was ID'd. And really, that's the bare bones model. So a Tekla model isn't just about the steel, you have to build all the detailing on top of that. And this kind of shows, I would say, the complexity of it. So you can see we're starting to instantiate some connection details. So each connection detail needs to be coordinated, it needs to be engineered, and it needs to be represented in 3D. The problem is, if you remember, you've got fabric on this model, so there's a lot of coordination, a lot of busyness going on. Another few screenshots. So as Tom said, we actually had to take some ownership of what we're calling the tertiary detailing. So every tab that the fabric was attached to, that was also brought and put into the Tekla model. We used Rhino and a Grasshopper script there to instantiate the tabs. And then now I think that was just exported as a IFC or IGES into Tekla. And then you can really start to see the complexity and the coordination needed. So we have a very basic primary structure. So we try to save costs by regularizing the primary structure so that it's just segmented. And then we put the kind of the expense in rolling the secondary steel. So the secondary steel is where we make sure we have enough curvature, we want to make sure there's drainage. And then all of this has to be coordinated. So I think you'll have some shots to show some that, right?
Yeah.
And very quickly, it's all very well being able to say, okay, if this structure is actually erected, we're comfortable, all the forces and deflections are adequate, but you have to think about how do you construct it. And you can see just from this rendered image that there's a huge degree of complexity here. I mean, how do you construct something like that? And having this ability to kind of label, ID, and group elements through a common kind of platform, it allows us to explore different erection schemes. So, much like in Revit, where you can filter and create work sets by attributes. If we know what our index are for some of these elements, we can start exploring different erection schemes. And the key thing here is, when you explore the erection scheme, you have to analyze it. What would happen if one of your elements is overstressed at this point? Well, you've got a problem, right? So sometimes your erection sequencing can control your member sizing. And the way we approach this is to set up what we call a stage, and then we do a staged analysis. So you literally think about how you want to construct it, and you go through all these different stages, one after the other, to make sure your stresses are adequate. And I think the image on the right kind of shows the erection sequencing going on for the installation of secondary steel.
Yeah, no, so this conversation involved obviously Walter P. Moore trying to help analyze all the shoring towers. Midwest Steel was the company that Banker hired to erect it, and at this table we were all talking about okay, the fabric's going to start to go in, the shoring towers are going up, the enclosure is up, and you start to see some of the booms and the lifts. At one point there was like 60 booms in this thing, so it really just kind of. Obviously we don't normally worry about means and methods, but this thing was so complicated and we had such a fine line of precision based on time and complexity. We really kind of inserted ourselves in that table, obviously assuming some risk by being part of that decision making.
Do you want to talk about this?
This is just a drone footage of the steel going up. Again, just to kind of orient everybody, we're on the south end of the facility. The large mega doors occur in this zone here at the bottom. The amphitheater is in between the two facilities. At this point, there's only 3 trusses left to go up, so we're making tremendous progress. And that's just more complementary. You start to see the folded ends of the facility were one of the hardest parts to go together, which is on the far left-hand side of the picture. So that's what you start to see, these things kind of hanging out there unconnected. But the beautiful thing about it is because of all the time and investment we put into it, I mean, no joke, this thing went up and every single piece fit. You know, obviously they had to hammer some things in, but we had 2 columns that were cut from the factory too short, so they had to splice them together. And of course, Banker Steel was like, hey Tom and Aisha, Joe, like, can you come check this out? Like, is this okay? I mean, it's going to be 70 feet in the air, nobody will see it. And we're like, yeah, yeah. They showed it to us, and we worked on it. So these are the cleats on the picture on the right. You see the cleat. That's how they tie the fabric. So they're like little boat anchors, and they bring the fabric in there and they bolt them together and they pull them taut. But there, I think at the end of the day, there's like 86,000 like cleats in the project that, as Steve mentioned, they modeled every single one of them through a script, a Grasshopper script, based on spacing and tension. And then you start to see the rolled members of the gray rolled members. That's what in the rendering you saw the white fabric with the gray strips. That's what that is. So the fabric went in after all of this, which was, can you imagine being in July in Florida, being on a roof and installing fabric? It was crazy for these folks. So here's 2 panels going in. It's a Shearfield 2. We did them in long strips. They came in like 24 feet wide or so by X long. They could be as long as they wanted to, as opposed to we did strips because twofold. Number one, we talked about the failure and the collapse strategy. We analyzed if a panel collapsed. Clients are always worried about if a fabric roof collapses, right? Like the whole thing happened, like Reliance Stadium had a collapse many years ago. It was disastrous, right? So we did this, so again, the owner got an insurance break on their deductible because we proved they were able to use our analytics to take to their insurance company and say, hey look, if we have a panel, it's only gonna cost 20 grand to replace, not 60 million. So then here's a drone footage of the fabric going in. The amphitheater's at the top of the page. Along the way, we started to kind of prioritize completion of the project. They had concerts lined up for May 27th, Memorial Day. Tedeschi Trucks Band was a local band in Jacksonville. They were going to open the thing, so we wanted to make sure the amphitheater was good. So you start to see that happening on the north side or the south side. Or the north side of the facility, top side of the page. But then we kind of started skipping around because this was, I'll be honest, it wasn't intentional, but it was a beautiful intentional thing. We started skipping panels on installing, so that's why they're scattered. And the reason it ended up being, then we followed that. So then next we went to the corner and we bounced around because the fabric comes like tan originally off the shelf, and as the sun bleaches it, it turns a white, like a beautiful white, this color white. And on the underside, go back a picture. On the underside, you see it's like that tan, right? So we didn't want like half the building tan and half the building white, right? Because it only takes like 30, 40 days to bleach out the fabric. So we started skipping around, so on opening day, you could see some, patterning happening, which was a kind of an interesting coincidence. So Steve mentioned like the detailing, the waterproofness. Obviously, I mean, as the architect and the project manager, every time the president of the team would be like, everyone keeps saying it's a stupid idea to put the roof on the underside. Like, are you sure you want to do this? And we're like, yeah, like we can do it. And he's like, is it going to be watertight? We're like, we'll figure it out. We'll make it happen, And even at one point, it became such a product of the conversation. We even approached them and said, listen, the contractor's saying if we put the roof on the top side, we could save $5 million. Do you want to do it? And Shad Khan's like, no, I want to keep it like it is. So then we had to take and develop, these are the V columns that come up through the building, and we had to design and fabricate these big boots that go around the column so that we could create the cleats around the column so that the fabric could tie for water tightness. So this is an example of a rendered Tekla model version that we ended up giving to Banker.
Yeah, and I think the digital model kind of really helped iron out any coordination issues that we could see before we.
I mean, we found a lot of different things. Like we have these long longitudinal trusses. They're 430 feet long at one point, and there was a little bit of an error between how they converge and how the water drainage pattern comes in, and we were able to use our Rhino model and do clash detection. We did some Navisworks stuff just from an MEP standpoint. I mean, like I said, MEP on this was very small as a scope of work, but the Rhino model allowed us to really kind of clash the fabric and the steel together. These are just good screen grabs of like, you know, the cleats and the boat ties and how they're pulling the fabric together. And so basically you had the secondary steel and you had these boat tabs on top of it, the fabric tied into it. Then you had about an 18-inch gap at top, every one of those secondary steel members. Then they came back and they had to cut and put fabric flaps on the top side and weld them together. So you can weld fabric no differently than like, well, it's slightly different, but so they weld the fabric down to the other fabric to complete that water tightness. But again, this is just, we had like 2 drawing packages, right? Like we had well, 3. We had this landscape and civil stuff, right? We did all our early work stuff, that was permitted. And then we did a GMP package that had architecture and MEP stuff, traditional. And then the 3rd package was a book, 11 by 17 book of nothing but details, to all of this stuff that was turned over as part of our record documents. This is a topside view of the fabric, so you're on the roof. I mean, the roof fabric it's as strong as metal deck.
It's really strong.
I mean, it's you know, this is Marty standing on it, and to the far picture, Marty invented this little thing that he can roll around on the roof, and he can test the tautness of the fabric, because that's a big deal. You know, if you get a bunch of wind billowing up on this thing and it's bouncing, you know, that's a problem. So they designed for you know, the right pressures for and strengths, and Marty's up there, you know, him and another dude up there just checking it out, testing it. All of those values that he's monitoring were the point cloud data that we had on the spreadsheets. So he was able to just real time look at it and be like, all right, this is supposed to be X and it's Y. Contractor, you need to go up there and pull it tighter. Just as a simplification. Some good construction photos, just kind of showing, you start to see the brow happening. The image in the middle is like nearing completion. There's one more diagonal that closes it. The far right one is the coolest image, I think, in my opinion, because it shows the exposed nature of the scoreboard. And the big scoreboard is, you know, 120, 30 feet long. And then the little building in the bottom is the back of house building. That's where the artists go, the green rooms, dressing rooms, that kind of stuff. And the loading dock is the little notch. Some better images. You can see how close it is to the water. When Irma came through, the whole ground, this thing was completely underwater. So, you know, and then obviously with the wind. Here's 2 construction photos of the skin and the brow, so you can see the openingness of the doors. So the white, or the whiter material of the roof is that shear fill fabric, fully constructed. And then the gray is the Versailles wall fabric, made out of Germany. First time we ever used this, so we had to go through. I don't know if anyone's from Florida, but you know, you had to get FPA, Florida product approvals, and NOAs, and you know, had to do fire inspections and all this stuff, and so we did all that real time using our model and giving it to the folks to do it. This is the inside. So again, it's practice facility for the Jaguars. This is the inside the facility looking towards the south wall. The 4 panels in the middle. May I borrow this real quick?
Yep.
This panel and this panel slide that way, that panel and that panel slide that way, and it's 220 foot wide opening, 58 feet tall, so it's very, and then on the other side there's a 60 by 60 opening that slides to allow the amphitheater to both be an amphitheater for the show, and then they can flip it around, do a 180, and then they can have, like, I don't know, a car show or a boat show in the covered Flexfield and have a stage to be able to use. And then the sports lights are up here because you know, they do practice at night. Wall pads for player safety. Here's a picture of the completed project at Tedeschi Truck Span. So this is the amphitheater. You remember that rendering that we did early on? I mean, it came out really, really, really awesome. You start to see how eccentric the roof is with the ribs. You have all the aisle lights and the dramatic lighting and thematic lighting. The proscenium was a project all of its own, which was really cool. The stage structure, the proscenium, we hired a company out of Canada, Triadetics, and we basically said, here are the parameters. We designed it, we modeled it, we wanted it to be a space frame, we wanted it to be all encompassing, and then we worked with them within our Revit model, and they kind of helped us. Okay, well, if we do this, we do that, and we can save some dollars because these things have piles that they sit on, because we're the floor of the stage, or the floor of the pit, this area here is 5 feet below sea level. I mean, it's on sea level as it is, so we had to go down, so hydrostatic pressures and all that stuff. So this thing's sitting on big piles, like 80 feet deep. And then you have these little interesting bullpens. We created little couch lounges out here. Here's Daly's Place is the branding partner. That's the back of house. So back in this zone is where the purple is, that's the other door. So if you take the stage away, that door slides back this way and you have a view into the covered flex field, so they can use this stage for the flex field. And this view here, by the way, is from the third deck, farthest away from the stage. And I sat up there, and it's the best seat in the house. I mean, it's incredible. You're only like 140 feet away. It's like being in Radio Music City Hall. And then probably the coolest view is that guy. So the whole roof, on top of the sports lights, the whole building is lit up with RGB, LED lights, so that Jaguars can convert it to anything they want. It can, it can flash, it can strobe, it can change any colors. But this is the best photo I have because we don't have all our professional photos taken yet. But it's really dynamic because the whole thing lights up, including the box. I don't know why they picked purple this time. But that shows this is probably the best view of the roof underside the steel fabric. And I believe that's it. But if anyone's got any questions, we would love to answer some. Yeah, man.
Just speaking about this slide, so does the light show up on the other side of the fabric?
So the question was, does the light show up on the underside of the fabric? It does a little bit. It's perceivable, but if all the lights on the inside of the facility were off, then you would see it. But there's enough ambient light that you can tell it's there, but it's not as dynamic as that. Well, yeah, but the shear field product is pretty thick, right? So you could tell there's something. You could tell that. So it's only 11% transmittance. So you could tell a little bit. Like if you knew it was purple, you could probably tell it was purple, but it's not distractive. In fact, Live Nation is the operator. They are very, very conscientious of two things: acoustics and light intrusion. So these scoreboards have these big lights on them right here, and they light up all these banners. During a show, they have to shut that off. So then we had to go through this whole promotional campaign with the Jaguars and call Publix up, who's a grocery store, and say, "Sorry, dude, during the show, you're not getting advertised." So, yeah. Yes, sir.
You made the wind analysis on the construction stuff. What about the surroundings? That's also one big concern.
Surround like the rest of the landscape? Yeah, so how big was the question was the wind analysis, not just on the building, but like on the whole site proper. BMT built a model and it encompassed how much real estate? Like, it was like 200, 300 feet of the whole site. So, like, let me show you. Let me go back. Let me see if I can get there. They did a pedestrian comfort. Aisha worked on the project with us. She was in our New York office. So they did a pedestrian comfort. Come on. There it is. So they built a whole model to the adjacent, so this is the adjacent businesses all the way. They built it all the way out to the river. They built the whole football stadium, and they built it all the way to the west, which is, I mean, that's a pretty significant lot. I don't know how many acreages it is, but it was pretty intense. Additionally, we had to do an acoustical study, and then we had to prove that the noise would not affect the people across the river because there's some residential neighborhoods. Anything else? Yes, sir.
What's the estimated life of that fabric?
I think it's warranted for 15 years, but they were very Shearfield. Again, it's a Canadian company. I think they're comfortable at 20, 25, but the moral of the story is 15-year warranty.
Yeah, I mean, PTFE is a lot more than PVC. PVC is like maybe 10 years, but PTFE, they actually don't know how long it'll last for. There's a project in California where they installed it in 1970 and it's still working.
But they gave us a 15-year warranty.
So the owner plans on a change out in 15 years?
I mean, we consciously talked about it. Like, the other thing that we didn't talk about is all the steel that was painted and treated, right? Like, the bigger conversation was, when am I going to have to go up there and paint this steel again? And how hard is that going to be? And how much is that going to cost? So, yeah, I mean, they know that the city of Jacksonville has a money set aside for facility-owned facilities for maintenance and maintainability, and that has been part of it. So I would say yes. Yes, sir.
You mentioned earlier about flooding. The area was flooded.
Completely.
How do you get
Well, we accounted it for the first time. So, you know, the whole floor of the amphitheater it's got a vault. It's got full hydration underneath it. So for hydrostatic pressures, the water gets pumped to a different vault, and those vaults go to a different stormwater basin. So it flooded during the event, but within 2 days it was clear. Yes, sir.
When it comes to replacing that vent, how long is your downtime on that?
So, to be honest, you shouldn't have to replace it. I mean, it has been engineered, so that should never happen. But, I mean, we did consider what would happen if it would fail. But that we say that's an extreme load event. It's unlikely to happen. And
I mean, I would even further say that if a panel failed, you wouldn't have a down event, because you can walk on there, you can get up there, you can manipulate. All the FANUC replacement would be done from the top side anyways, for the most part.
Mm-hmm.
Maybe there's a cherry picker from time to time, but I wouldn't say you would have any down
If
event.
it was to happen, you'd be out like what, a couple hours or a day?
no, I mean, a week maybe.
But I'm saying,
I mean, if it was a significant thing, it would probably be a week or so. But I mean, I don't know. We're speculating because, like you said, it's not supposed to.
Yeah, I mean,
They were doing everything on the field while they were building and putting the fabric on. So theoretically, it should be pretty seamless. Pun intended. Anything else? Well, cool. I appreciate you coming. Thank you.